This is page 13 of the fault tolerance notes, and we're going to look at an example with two levels of recursion. So n is going to be 7, m will be 2. So we got 7 generals, 2 of which are treacherous, and let's just start drawing this thing. So general 1 is the commander again, and it sends its attack command to generals 2, 3, 4, 5, 6, and 7, and we're going to be drawing a lot of messages, so I'm just going to use the ellipses. It's the same thing being sent. Now what I didn't say is in the paper is that each message is prefixed with the number of the general that's sending it. So let's just say again that general 1 is saying to attack, so we put a 1 in front of that. This will become useful later. Now I'm going to call C the number of messages. C stands for communication, so the number of communications in this case will be 6, or n minus 1, and this is our initial condition. And now we start to go into the levels of recursion. So Lieutenant 2 receives a value, and it's going to implement OM2, which means that it's going to send messages to Lieutenants 3, 4, 5, 6, and 7. I'm squeezing this in a bit so I can fit information on the right. And again, the value that it's sending is going to be the same to each of them. So it's going to prefix its number to 1 attack, to 1 attack to each of those messages. Well, let's draw the other end here. So 7 is going to be sending its messages to 2, 3, 4, 5, and 6. And let's say, for example, that general 6 and 7 are the traitors. And so the message, or the value that it's going to send here, is going to be 7, 1, R. Now, really, these are representing faulty components, which can present different values to different observers. So maybe sometimes it will send attack, sometimes it will send retreat, other times it will send nothing at R, but just to keep this straightforward, I'm just going to assume it sends R, same as 6. I'm going to put the number of communications over here. I want to leave the left side empty. So the number of communications is going to be 6 generals sending 5 messages each, and let's just show what each message each lieutenant general has heard. So Lieutenant 2 did not send itself a message, but it heard from Lieutenant 3 what Lieutenant 3 says, or General 3 says what Lieutenant 3 says that General 1 said, which is to attack, and will receive 4, 1A, 5, 1A. And remember, 6 and 7 are the traitors, so 6 will say that 1 told it to retreat, and likewise with 7. Okay, so each lieutenant is going to have a vector of values that it's received. So Lieutenant 3 will have heard from Lieutenant 2 that Lieutenant 1 told it to attack, nothing from itself. Then 4, 1A, 5, 1A, 6, 1R, 7, 1R, and so on up to Lieutenant 7's vector. And again, Lieutenant 7 is unreliable, so who knows what would be in that vector of messages. So really, there would be enough information in this example for the faithful or the loyal lieutenants to arrive at the correct decision. But there are scenarios where, for example, if the general is faulty and it sends different messages to different lieutenants, that they wouldn't all arrive at the same conclusion. So this example does not show why the extra level of recursion is necessary, but shows how it would work. So then we have another level of recursion where Lieutenant 3 has received a message and it acts as a commander and sends it to the other lieutenants. And a message that has the number of a general in it never goes back to that general. So what 3 is going to send here is 3 heard that 2 said, that 1 said to attack. And then 4 will likewise send out 4 messages and so on. So what we're going to have is at the second level of recursion, we've had 30 messages sent, and those are going to trigger an additional 4 messages each. So the number of messages here is 6 times 5 times 4 is 120. And now what we're going to have is basically each lieutenant will have a table of values that is received. So let's look at what those values look like. I'm going to make this a little wider just so we can fit in the values. So there's going to be 6 rows, 6 values each. And that will be Lieutenant 2's table, and Lieutenant 3 will have its own table, Lieutenant 4, and so on. And so there's going to be 6 tables. We've got 120 messages sent, so there should be 20 messages in each table. Now you can see this is a 6 by 6 grid, so there's going to be 16 that are missing. And so each row represents what's been heard, I guess, third hand from a lieutenant. So we're going to skip the first row for now. The second row is what Lieutenant 3 is reporting. And so Lieutenant 3 will report what it heard from Lieutenant 4 heard from Lieutenant 1, which was attack, and what 3 heard from 5 heard from 1, which was to attack, and then what 3 heard from 6, and remember 6 is lying, so it's retreat, and same goes for 7. And next we will have what Lieutenant 4 has heard. So Lieutenant 4 heard from Lieutenant 3 what Lieutenant 1 said. Now the diagonal is going to be empty, because those would be the values where, for example, 4 said that 4 heard from 1, and we're not sending those messages, so we skip that, and we get 4 heard from 5, heard from 1 to attack, 4 heard from 6, from 1 again to retreat, because 6 and 7 are liars. And keeping going here, next row is what 5 reports that it's heard from the other lieutenants. So 5, 3, 1, 5, 4, 1, 5, 6, 1 will be retreat, 5, 7, 1 will be retreat, and then we have 6 heard from 3, heard from 1 to attack. Actually, the value coming from 6, so the value coming from 6 will be unreliable, so these will all be retreats. So 6 will say that it heard from 4, that it heard from 1 to retreat. 6 will say that it heard from 5, that it heard from 1 to retreat, and will report that it heard from 7 from 1 to retreat. And similarly for Lieutenant 7, it will say that it heard retreat from each of them. So now we have 5 rows of 4 values. So Lieutenant 2 has received 20 messages, and Lieutenant 3 will have a similar table. So what we've got missing here is the diagonal, but also, and so for example, Lieutenant 3 wouldn't tell Lieutenant 2 what Lieutenant 2 had told it that it said, and Lieutenant 4 likewise wouldn't do that, and Lieutenant 2 also does not have a row where it tells itself what it heard from the others. But that's going to get filled in here. So in the last level of recursion, Lieutenant 4 is going to just repeat to itself or use the value that it heard from its commander. It's using the value 3, 2, 1, attack. Now I don't want to draw out Lieutenant 3's table, that would be painful, so we'll just fill in what values would be inserted into Lieutenant 2's table here. So we would have 2, 3, 1A, 2, 4, 1A, 2, 5, 1A, 2, 6, 1R, 2, 7, 1R. And there's no communication in the OM0 algorithm, it just uses the value that it was told. So now we're going to come out of the recursion. So for step 3, so this would be step 3 of the recursive algorithm, whereas this here was step 2, it's going to take the majority value in each column. So what Lieutenant 2 will compute is the majority of each column. So we could say that is taking the majority of the 3-1 column, the majority of the 4-1 column, the majority of the 5-1 column, majority of the 6-1 column, and the majority of the 7-1 column, and these will be the values that it uses. So the majority, and the first column is not filled in yet. So the majority values here, we've got attack, 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 retreat, retreat. So this will be attack. For column 4 it will be attack. For column 5 it will be attack. For column 6 it will be retreat, and for column 7 it will be retreat. And for the last level of recursion, let me just go back up here. This was step 2. We recurse out, and this will be step 3, and the value that L2 will use is the majority of what it heard from the general in the first place, plus this these majority values above. So we'll call that the majority 3, 1, majority 4-1, majority 5-1, majority 6-1, and majority 7-1. And so that will give us the majority value of attack, 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 retreat, retreat, which will give the decision to attack. And so Lieutenant 2 is loyal and it will reach the right decision, as will Lieutenants 3, 4, and 5. So that's how this algorithm works. And again, I haven't demonstrated why you actually need that last level of recursion, but there are cases where it is necessary. So this Byzantine fault tolerance allows us to know that the loyal participants will end up taking the correct action in the presence of a maximum number of faulty components. But it's pretty expensive for communication. And so that's the end of the section on fault tolerance.